Right, so we're going to talk about how atoms produce light and how this relates to our flame test lab that we did earlier this week. First of all, what is light? Light is just a form of energy, just like sound and heat and other forms that we've talked about and that you've heard of in the past. Light can be considered to exist in two different ways. The first is as a little packet or a little ball of light called a photon. And then the other one is actually as a wave, which is when the photons go and they kind of travel together. So just like a ray of light or a wave of light. Now that wave is actually a sine or a cosine wave from math class. It's not a straight line. So that's why they refer to that as a wave. To measure different lights, we use what's called a spectroscope, and we used this in lecture while we were talking about these notes. A spectroscope has a prism inside of it, and it actually separates the light so you can see all of the individual colors. We went ahead and aimed the spectroscope at a white light. When we went ahead and did that, we saw what you guys described as a rainbow. So you guys can see here with this black background over here, you guys saw this with your numbers 4 through 7 up top. So that just refers to the wavelength, which we'll talk about in a second. So you guys can see all of the different colors here. This is actually called a continuous spectrum on your note sheet. And that's because there are no blank spots in the spectrum. So it goes all the way from red to purple with no breaks in the spectrum. One thing I do want to point out is down here you guys can see that this section where we can see the visible light and all the different colors is one small part of what's called the electromagnetic spectrum, which is this larger thing, and it goes all the way from radio waves in low energy all the way up to x-rays and gamma rays up at the higher energies. Now, this continuous spectrum existed or exists when we're looking at white light, and that is because white light is made from light bulbs that actually have a solid piece inside of them. So this is my light bulb, and it has the little electrodes with the filament in between here. So you guys remember way back when they had these types of light bulbs, and if they broke, you guys could shake them, and you would hear the little rattle. That's the broken filament inside there. But the continuous spectrum exists because as this solid filament gets heated, all of the atoms move really, really fast. Now, remember, it's still a solid. So if we wanted to draw atoms of a solid, you guys know that they are really, really close together. You guys know that they're not moving location per se, but they are still moving. They're shivering in place. If I now heat up this solid, it's still a solid, but it's moving even faster. When it moves really, really fast, the energy is given off and the atoms are still constantly vibrating. Because of that vibration, you guys can see all of the colors of the rainbow instead of just specific sections. Excuse me. So that's where the continuous spectrum or the rainbow actually comes from with this white light. Now, another type of spectrum that we saw with the spectrometer or spectroscopes is when we looked at a fluorescent light. So when we looked at the fluorescent light, we saw a spectrum that looked like this down here. So you guys can see that there are gaps in between the colors. You can see that not all of the colors are being viewed here. You can't see any purple. You don't see orange or yellow, and a little bit of green blue is also missing. So the reason, first of all, this is called the bright line spectrum. It has a second name, but typically it's referred to as the bright line spectrum. So this bright line spectrum comes, again, only certain photons are being observed, and that's because each color on that spectrum corresponds to a different energy value. So what that's basically telling us is that only certain energy values can exist, which means that this can be explained by the movement of electrons, as you see here. If you take a look, this electron over here starts out in the second energy level, and this purple squiggly line, which I'm now making yellow, goes ahead and excites that electron. So it actually jumps up and gets energized. So now it's in the third energy level. So you guys have all heard the phrase, what goes up must come down. When it comes back down to its original state, that amount of energy that was added to it comes off, and it comes off or is emitted in the form of a light. Now, like I said before, the different colors are given off because of different distances. So if the electron is traveling just a very, very small distance, that's what gives off the red color. A little bit more of a distance is a greenish blue color, and the highest energy that it can give off would be giving it off in the purple color range. So those are the largest distances that the electrons then travel. Moving on to the atomic emission spectrum. Now these are all seen, this is another bright line spectrum down here, and these can be seen for every element on the periodic table. Now the one that we saw with the fluorescent light bulb, this one down here, is a little bit more blurry than a typical emission spectrum, and that's because fluorescent light bulbs have multiple different types of gases in there, so it's not just one element. If you look over here, we have a emission spectrum, or a atomic emission spectrum. Basically is the exact same thing as a bright line spectrum, but it's a lot more clear. There's only one element being shown here, and it's only sodium. So if you take a look at sodium's emission lines, you can see that there are two of them. They're both yellow. Down here around 630, 640-ish. The reason that when you burn sodium, it burns yellow is because of this. So the electrons are being excited, and when they get excited, then they go back down to their original states, or original energy levels, and when that happens, they give off enough energy to be in the yellow section of the emission spectra. If we go to a slightly more complex molecule, or element, which would be copper, you guys can see that it gives off more emission lines. So there are actually 8 lines in the copper spectrum, all the way from this purple line that's really, really hard to see to the brighter yellow line. But if we were to take all of these lines and all of these colors that are given off, mix them together, that's what actually gives the green color that you guys saw in the lab. This page just shows you a few more atomic emission spectrums, which, like I said before, are just called bright line spectrums typically, but these are for different elements. So this top one is the simplest one of the 4. This is actually hydrogen, so even though it only has 1 electron, it can jump and move 4 different ways. So it can go between different energy levels and create 4 different colors, or 4 different energies of light. The second one here is actually helium. So that one has 2 electrons. It's a little bit more complex. The third one down here would be mercury. This one has 80 electrons, but you can see that there aren't 80 different lines. So at some point, the electrons can only move, and only certain electrons can move in the atom itself. The very last one down here is uranium. That one's probably one of the more complex ones between any of the elements on the periodic table. You can see a lot of different colors and a lot of different lines given off, but it's still a bright line spectrum or atomic emission spectrum because you can clearly see the lines. It's not fuzzy. You can see the gaps that are not being shown as well. Now, moving on to the different wave properties of light. So before this, we were talking about light in individual packets of energy that are given off. If we talk about or light as a wave, there are four main properties, the first of which is speed. All light travels at the speed of light. It doesn't matter if it is a X-ray or the lowest infrared colored light possible. It's all the same speed that it's traveling, and that speed is 2.998 times 10 to the 8th meters per second. So that is 299 million meters per second, and way faster than the speed of light, way faster than the speed of sound, or the or anything that our eyes would ever be able to see. The speed of light has a symbol, which is letter C. Again, it's a constant, so that's an easy way to remember that speed of light is letter C. Now, that's the only one of the wave properties that's constant for all light. The other ones we're going to talk about now are changing for the different colors and the different energies of light. So wavelength is a common thing to talk about. This is how our spectroscopes actually measure the different colors that are given off from the lights that we study. So wavelength is actually denoted with the symbol lambda. It's a Greek letter L. It looks here like an upside down Y. But this is just showing you that wavelength is the distance between two peaks of the same wave measured in nanometers. So nanometers are super tiny. We talked about them at the beginning of the year with our conversions. There are 1 billion nanometers in 1 meter. So that's to hopefully show you how tiny those are. But again, wavelength is from one peak to the next peak on that same wave. You can see by the picture up here that the red colors have a longer distance between those peaks, or a longer wavelength, than, let's say, the blue waves over here. They're shorter wavelengths because there's a shorter distance between those peaks. If you look at frequency, frequency is actually this symbol here. It's kind of a funny looking V. When I draw frequency, I draw it with it's just a V with a tail in the front. It's a Greek letter nu, and that's just showing us the number of waves that pass per 1 second. So it's measured in units per second. So if we were to say, okay, all of this red portion of the wave that's drawn here shows up within 1 second. So we could say that would be about 2 waves per second. If we did the same thing with the blue waves down here, you guys could see that there are a lot more waves, and if we assumed that this blue section was all transmitted per 1 second, it would be about 8 or 9 waves per second. So that's showing you that your red frequencies are lower or a smaller number than the blue frequencies, which are higher. With this, you guys, I'm hoping, can see that wavelength and frequency are actually inversely related to each other. So it says that at the very bottom. And something else that was inversely related that we studied at the beginning of the year was Boyle's law with pressure and volume of a gas. When we looked at Boyle's law equation, we knew that it was multiplication that we used to solve those formulas or those types of problems. So it's the exact same thing when we're looking here at our formula for frequency and wavelength. Down here at the very bottom, I have the formula for you. So C equals lambda times frequency, or lambda times nu. Now, those or that formula has a c in it. So remember, that is your speed of light. So if I have the wavelength and the frequency of a certain type of light and I multiply them, I should always get that same constant or speed of light, which is close to 300 million meters per second. When we add energy into the formula, or when we get energy formulas with our wavelengths, we have to include another constant to kind of correct for that formula. One thing you want to remember from your written final last semester, when we were talking about our energy and food, energy is measured in joules. So remember, that's abbreviated just with a capital J. And that constant that we have to add to make our formulas work is called Planck's constant. It's just listed after somebody who discovered the constant. It is 6.36 times 10 to the negative 34 joules per second, or joules times seconds. Now that is a super tiny number, and if you remember how tiny those wavelengths are, it's getting even smaller now with this number here. So one formula that you should know for energy is equal to Planck's constant times the frequency. The other formula that I want you to know for energy is equal to Planck's constant times the speed of light divided by wavelength. So another way to write that one, just so it's a little bit easier to see, you can see it here. H again is Planck's constant, c is your speed of light, and lambda is the wavelength. So depending on if I give you wavelength or if I give you frequency, you'll want to know which of these two formulas to use. The last thing I want to talk about is quantums and photons and what's actually happening here. So again, we've already talked about a photon, but it is just a name for a quantum or a quantity of light. So remember, a photon is just a little ball of light that has a specific energy or a specific wavelength tied to it. Electron transitions are when those electrons that are in your atom, so if I were to draw an atom here with your nucleus and your energy levels, and you remember that you have electrons on those energy levels, when the electron is moving between energy levels, that's an electron transition. So when it goes up to be a higher energy level, that means it's moving away from the nucleus, and a photon has to be absorbed into the atom. Now, if I were to go the other way, and I start with my electron on this higher energy level and I come back down, it doesn't always have to go to the ground state, maybe, or the first energy level. Maybe it just goes to this one. But regardless, when it comes back down, a light is being emitted from the electron, or from the atom. So a photon is being emitted when the electron moves closer to the nucleus. Now, the last couple of things that you want to know is just ground state and excited state. You can see it here in my picture. If I were to tell you that my electron naturally occurs where this green electron is on this first energy level, then that's what we call the ground state. If my electron that naturally occurs on that first energy level gets energized and ends up on any level above that first energy level, that's called an excited state. So anything above a ground state would be considered an excited state. Now, I hope that this video helps you try to get the light information through your head just a little bit more. Remember, you can always come back to this and review this video as you see fit.